Welcome back. So this session here is a continuation of our previous session. In our previous session, we were looking at the Steel Construction Manual, I think the 15th edition here, right? So Steel Construction Manual, we were looking at 15th edition, and we were looking specifically at easiest section, which is the design of tension members, and then we looked at details like how um, a net effective shear lag factor U gross areas can be calculated, right? And we also looked at how PPN or PPT, which is the minimum of um, the yielding strength and rupture strength, how these things can be calculated. Okay? So yielding, so this is nothing but the minimum of yielding happens on gross area. So P times the Fy and A gross, whereas rupture happens on net area, so that's where Fu and AE or A effective net area come into the picture. Okay, so we talked about all these things. We did a couple of worked out examples. If you have not watched the previous session, go ahead and watch it. But then we ran into a peculiar case wherein, let's say, you have a tension member and then you have staggered holes like this, right? If the holes are staggered, then how will you calculate your net area? Maybe the section will crack, so that is one path. There might be another path which is like this, then like that, it goes like that, and then comes like that. So this is 2, 2. This is another failure plane. So we were trying to do those calculations. So when it comes to this breadth level problems, you will be given a slightly. These problems can get the level of complexity can be from medium to high. You will get on the breadth level exams, you will get simple problems, and that is the focus of this session here. Okay, so let's get started. I think part 5 is where the gross and net areas were discussed. So if you open that section, part 5 here, you go to gross area section. Um, they don't give you calculations here, but they refer you to either that section or um, or a slightly different section here. So effective net area is being calculated here in a different section. Okay, but if you go to um, chapter B, which is that one here, right? And then you go to properties here. So if you go to this particular section B4, and gross net area, that particular section there, there's an interesting description about how net area has to be calculated. Okay, so net area um, has to be calculated for a chain of holes extending across a part. For example, you have a hole like that, and then you have a chain of holes. They can be either straight or they can be zigzag. I mean, if you let us say this is your case, right? The bolts are staggered. Then there is one dimension which is called S, and there is another dimension in this direction which is called the gauge. And here is the direction of the loading. So the dimension parallel to the direction of loading is called S, and that is distance between this bolt hole and that bolt hole in this direction. And there's a dimension G which is perpendicular to S, and that is in this direction. Okay. So given S and G, then you can calculate your net area um, as follows. So what you do is you take a net is a gross minus. Um, For example, let us talk about this particular scenario here. Let's talk about this particular scenario. You have two bolt holes, so 2 times of TH times of thickness. That's about it, right? Whereas if you're talking about, let us say we're talking about this path here, I'll draw that in black. Let us say that is the failure plane, okay? So that for that failure plane, you calculate A net as A gross minus, you deduct one, two, three holes. So you deduct 3 times the diameter of the holes, but you come back and add a term called S square by 4G, and you add one for this limb and one for that limb. So 2 S square by 4G. So that's how you calculate your A net um, for a zigzag path like that. Okay. Again, just to be clear, let's say you have a bit like that, and then you have holes like that. Right? Okay. Let's say this is your plate, and this plate is subjected to tension. We are talking about two different paths. One, the first path is like that, right? And in this case, your net area is nothing but A net is you take the gross area of the plate and you subtract 2 diameter hole times of feet. Okay. Whereas if you're talking, let's talk about this path here to, let's say, cracks like that. Right? Let's say the failure plane is along 2 2. Then you need a couple of dimensions. You need the dimension, this dimension called S, and that dimension called G. Okay. Let us say this dimension is G1 and this dimension is G2. Let's say you have two different gauge distances. Then your A net is A gross minus, you have one bolt hole, two bolt hole, three bolt holes. So 3 times of diameter of the hole. But you come back and add 1 S square by 2G for this one, another S square by 2G for that length. Okay. So this S square by 2G is S is same S square by 2G1 because this distance here is G1, right? From that center line to that center line G1 plus you S square by 2G2 because for this limb, that limb there, this is G. Okay, that's how you compute your A net. Once you compute your A net along section 1 1 and along section 2 2, then you figure out which one is the least, and then you can run your numbers accordingly. Okay. So let's do a problem on this one, wherein we try to apply this particular. So that is what is written in this section here. Okay, so the net area AN of a member is the sum of the product of the thickness, sum of the product of thickness, and the net width, and then the net width of each element computed as follows. Okay, in computing the net area for a tension and shear, um, the width of the bolt hole shall be taken as 1/16 greater than the nominal dimension of the hole. But the nominal dimension of the hole itself is d bolt plus 1 by 8 in some cases, d bolt plus 1 by 16 in some cases, nominal diameter of the bolt. Right? And this is when your d bolt is diameter of the bolt is less than 1 inch, whereas if your diameter of bolt is equal to or greater than, the diameter of the bolt is equal to or greater than 1 inch, um, then this is the nominal diameter. To that, to these, you again add another 16. Okay, that's how you calculate your DH. So in short, DH is equal to D bolt plus 1 by 16 plus another 16. Okay, or DH is equal to D bolt plus 1 by 8 plus 1 by 16. This case is when your diameter of the bolt is greater than or equal to 1 inch. This is for a case where your diameter of the bolt is less than or equal to 1.0 inches. Okay. Um, now this is the section we talked about. For a chain of holes extending across a part in any diagonal or zigzag line, the net width of the part shall be computed by deducting from the gross width the sum of diameters or slots in the section of all holes in the chain and adding, right? So you're deducting something and you're adding something. What are you adding? You're adding a square root of g. So that is nothing but a net is a gross minus number of diameters times the whole diameter times thickness, right? So this is one area, but you come back and add s square by 4g, however many. Let's say you have m s square by 4g times the thickness. I think I forgot the thickness term in the last uh, in my last explanation. Okay, but just to be clear, this is area. This is number of small areas. Each area is diameter whole times the thickness of the plate, right? And this is an additional term that needs to be subtracted. Okay. If you are just finding out your effective width, then you just have to subtract the square by 2g and the diameter of the hole. But if you are finding out your effective area using the area formula, then you take the net, then you find out the net area as gross area minus subtracting this area and then this particular item. Okay. So let's do a problem here. Um, um, so let's say you have a plate like that. You have a plate like that. You have holes like that. Right? Then these are staggered. Then you have the same hole outside. In this plate here, discontinuous edge is subject to LRFD. Okay? Let's say the holes are for a bolt of 1 inch. So the diameter of the bolt is 1 inch in this case. Okay, and then these distances are given. Let's say this is 3 inches. Let's say distance from here to here is 5. From here to here is 5. And from the center line to edge is another 3. Okay, in the same lines, these distances are all given from here to here, from here to here, from here to here. These are all let us say 3 inches. Okay, in other words, they are giving you the gauge um, distance. So this distance is from center line to center line, that is 3. And the vertical distance are from this center line to that center line, so that is 5. Okay, so you can either, I mean, the question is just asking you to calculate the find the smallest net area. Find the smallest net area. Right. So one scenario is um, the a crack can appear like that. That is scenario one. So let us say this is A, this is B, and C, D, and let's say E. Okay. So let's talk about the chain A, B, D, E, and we calculate the net area along that direction. Okay. So before we do that, we need to find out what our DH is. DH is D bolt, the nominal bolt dimension plus 1 by 16, D bolt plus 1 by, since bolt diameter is equal to 1, so in this case it is 1 by 8, so this is nothing but D bolt plus 3 by 16. So D bolt is 1 plus another 3 by 16, that is 1 and 316. Okay. So now the net width is the gross width, which is nothing but 3 plus 5 plus 5 plus 3, which is 16 there, times the sum of how many whatever bolt holes you have. Correct? So we are talking about width, not area. So that's the equation. So it is nothing but 5 plus 5 plus 3 plus 3, which is 16, minus how many bolts do we have? 2 bolts, in this case B and D, and the diameter of each volt is 1 and 316. That is 188. Okay. So this would be 13.62 inches. Okay. But there is also another section which is let's do this color, which can go like this: A, B, and then it can go like C, then D, and then E. Okay. So for path A, B, C, D, E. So when you're going in that direction, again you have the net is nothing but the gross minus how many bolt holes? 1, 2, 3. So 3 times the diameter h, right? Minus 1 s squared by 2g for that limb, another s squared by 2g for that. Okay, and looking at the problem, s seems to be, if this is the direction, s is the direction. S appears to be 3 inches. G is, if this is your direction of loading, perpendicular to that direction, which is 5 inches. Okay, so that means you have to come back and add 2 such s squares by 4 times of g. Okay, so this is nothing but the total width is 16. 3 times of diameter hole 1.188 is 2 times 3 square by 4 into 5. You do that math, you'll end up with 13.34. Okay, so 13.34 is less than this width here, which is 13.62. So the lesser of these two will govern the result. Okay. So in if you have to do the area calculation directly, this is just the width. So if you have to find out the A net, then you take the 13.34, multiply it with the um, thickness of plate. I think in this case, thickness of plate is 0.75 inches. So you multiply that with 0.75 inches. Okay. If you want to do the area calculation directly instead of starting with the width, then what you do is you a net is a gross. We're talking about this case here. A gross minus um, 1, 2, 3 bolt holes, 3 times of the diameter hole times the thickness of the plate, plus how many s squared by 2g is 1, 2. 2 times of s squared by 2g 4g times the thickness of the plate. Okay, so that is nothing but a gross is your width, gross width, which is 16 times of 0.75 minus 3 times of the diameter hole 1.188, 1 3/16 plus gross also times the thickness 0.75 plus your 2 times of s is 3 square by 4 times of g is 5 times your thickness is 0.75. Okay, so this will also give you um, same number, so which is 13.34 times of 0.75, which is nothing but 10.0 inch square. So this here is also 10.0 inch square. Okay, so we end up with the same calculation. Here we did the width business, we found out the effective width and multiplied that with the thickness. Here we are just doing calculating the area directly. Okay, let's do one more problem, and that should add a little more clarity. So on this problem, what we have is we have an angle, a little more complicated than regular problem here. So we have an angle like that, and we have 2 bolt. It is connected to on this side 2 bolt holes, and the spacing from that is 3. Actually, let me draw the angle here. two bolts connected with two bolts on this side. Here is from here to from the center to that dimension. There are two bolts on this side. These are all staggered. From the center to here is 2.25. From here to here is 2 inches. Okay. So the angle is obviously connected to the on the left side is connected to aggressive plate. The right side on the top it is connected to aggressive plate. Okay. And this is a this angle is a L 8 by 6 by half. Okay. So one leg is obviously this leg is 8 and the other leg is 6 and this is half an inch thick angle. Question is pretty easy. Well, how do you determine EER? Determine LRFD design strength. Yes, it is a tension number. Question is pretty straightforward. It is nothing but area times of the stress, but then which area, what stress. That is what makes the whole thing a little more complicated. Okay, so when you have an angle like this you will have to unfold this angle. So imagine you cut this portion here. Imagine you're cutting this entire portion, and then you're turning it this way and attaching it up top. Okay. When you do that, what happens is, let's say this is the center line here. Here is your 8-inch leg, and this is the other leg. Right? So let's say that is the topping line. Okay. And then this is the discontinued edge of the structure. You have two holes here, and the hole pattern is something like this. Right? The same thing, you open it up, you have the same similar hole pattern up top there. Okay. Now the interesting thing is, um, because you're cutting it here and then turning it up and attaching it here, that leg, you lose one thickness in the process, right? So, so the most important thing when you unfold stuff like this is to find out what your gauge distance between this bolt and that bolt is, right? Because we know the gauge distance between this bolt and that bolt is pretty easy. That is just 2 inches. That is this number here. This is 2 inches. Whereas here, um, you initially had, the idea is to find, the question is to find this gauge distance. If you find that gauge distance, um, then the rest of the procedure is pretty easy. That distance is from here to here is like the center line of this bolt hole is like 3. So you have a 3, and from here to here, from that to here is 2 plus 2.25, right? But 2.25, but then you are losing one thickness because of this cut and paste job here. Okay, so you reduce one thickness, which is half an inch. Okay, so this whole thing comes down to 3 plus 2.25 minus half inch, which is 4 and is nothing but 4 and. In other words, I'll delete this dimension and then write, so from here to here is 4 and 3/4. Okay, from here to here is nothing but this distance, which is, I think from here to here was 3 inch. So that is 3 inch. Okay, so now we know the gauge distance between that hole and this hole, this hole and that hole and this bolt hole. So we know all the gauge distances along this direction. Now we have to find out in the problem definition this spacing from here to here, here to here, here to here, here to that center line. This is all even, and it is even at 1.5 inch. So this is 1.5, that is 1.5, and this is 1.5. Okay. So let's call this, give them some name. Let's say outer edge is A, this is B, this is C, this is D, E, and F. Okay. Let's talk about um, this path here, which is the most simplest, A, B. Located right there. Let's talk about this path here, which is A, B, D, and F. So, so this thing can crack like that. So that is one failure path. So we're talking about A, P, D, and F failure path. So for that failure path here, uh, A gross is A gross, sorry, A net is what you need to calculate. A net is A gross minus sum of DH times of T's, plus you come back and add M times of how many, depends upon what you have is squared by 4G's, right? So we don't have an inclined or oblique path, so this term will be 0. So you're just um, all that we need to do is find out our A gross and deduct 1 bolt hole, 2 bolt holes. So 2 times of DH times of T. Okay. So some side calcs AG for this member is gross area of L by L 8 by 6 pi and a half. You go to the table, you find out that this is 6.8 inch square. So that is AG. DH, the bolt hole diameter, D bolt here in this example is 7 by 8 inches. Okay, when D bolt is 7 by 8, this is less than 1.0. So DH is nothing but 7 by 8 plus 1 by 16. That is your nominal bolt hole plus another 16. So that would be 1 by 8, 1.0 inches. Okay. That's your DH. So that means A gross is 6.8 minus 2 times of DH is 1.0 times of thickness is 0.5 inches. You find out that this is 5.80 inch square. That is your net area um, along the ABDF path. Okay. Should we use that? I don't know. So we'll have to come back and calculate the net area for a slightly different path. Let's say that path is A, C, A, B, A, B, C, and then you go to EG, E, and then G. So we're talking about that path. Okay. So the path is A, B, C, E, and G. A, B, C, E, G. How do you calculate your net area here? Right? So the net, so for that path, your A net is A gross minus how many bolt holes? 1, 2, 3, right? So 3 times of the diameter, 3 diameter of the holes, but then you come back and add 1, and that's about it. 1, because there is only one oblique path, so 1 times s squared by 4g. Okay, so that is A gross is 6.8 minus 3 times of 1.0 plus s squared by 4g. S is this spacing is 1.5 by 4 times of gauge distance is that gauge distance, because we're talking about that path, which is 2 4g. Let's calculate that and see how much we get. 6.8 minus 3 plus 1.5 s square divided by 4 times of g is 2. So the whole thing comes out to be 2g. G. This is 2 and sorry, this is 2 and a half here, and that is 2 and a half. Okay, that means this is 2 and a half. So let's calculate that again. 6.8 plate is 0.5, correct? Then this into thickness of the plate is 0.5. So that is area, this is area, and that is also area. Okay. So just to be clear one more time, what we are doing is 6.8 is the gross area minus 3 times of diameter of the hole times of thickness of plate, right? Plus s square by 4 g times of the thickness of plate. So that is 6.8 minus 3 times 0.5 plus 1.5 square 4 times of 2.5. So that is 5.4125 inch square. So this was 5.8. This path you have only 5.4125 inch square. So that is your AM there. Okay. So the net area part is easy, but there is one additional detail here that we need to consider. That is very important. Net area calculation part is pretty easy. Okay. So if you see this path here, A, B, C, E, G, A, B, C, E, and G. When this happens, that path is only taking the load of, let's say this is P. That particular path is only experiencing the load from um, P times of 9 by 10, right? Because this particular bolt is taking 1/10 of the load. There are 10 bolts here, each bolt is taking 1/10 of the load. Since this bolt is not included in that path, so that particular path only gets to see 9 by 10 of net area. So, so you compute, you calculate. I mean, this is your load, and then you compare that with this net area, and use that load in your calculations, and this net area in your calculations. Or if you want to treat everything fair, what you do is you come back and increase this net area. So increase this particular net area by a factor of 10 by 9. So and then use that to compare it with all other paths and pick up the minimum value. So when you do that, you multiply this net area by 10 by 9. So that would become 6.014 inch square. Okay. So we figured we are done with the second path. So the net area for A, B, C, E, G. If you want to treat it, if you want to compare them with all of the net areas, then you need to bump it up by a factor of 10 by 9, so that you can compare it with this one, compare it with some other path that you have in mind, and then pick up the least value. Okay. So now let's do one more net area computation, that is for um, this path here. That is, let me do that in highlight. So A, B, C, D, E, and then G, like that. Okay. So if the crack is, the failure plane is that, how do you calculate your net area? So the failure plane is that, then what you do, your net area for this is for A, B, C, this is C, right? This is D, D, this is E, E, and then um, this is G, right? G. So net area for that is nothing but the gross area AG minus how many holes do we have? 1, 2, 3, 4, minus 4 times of diameter of the hole times of the thickness of the plate. Plus you come back and add how many s square? 1 s square by 2g for that path, which is s is 1.5 constant square by 2 times, sorry, 4 times of g is 2.5 for that path, right? This is g. plus then this one for this path here, your G is 4 and 3/4. So 1.5 square by 4 times of 4 and 4.75. And for this oblique path here, your G is 3. 1.5 square by 4 into 3. So if you do that, you find out that your area is 5.065 inch square. Okay. For this path, you don't have to bump up your load because it is cutting this, that, that, and that. Okay. So looking at this, if you look at this, the least A net is for this path here, and the A net for that path is 5.062. So this was 5.8. The bumped up value for this one was 6.014. So the least value is this one. Okay. So now that we computed our A net, or let us write it down. Um, so A net is minimum of different A nets that we computed. The first one was 5.80. The second one was 6.014. The third one was 5.065. These are all inch squares. Okay. So that means A net is equal to 5.065 inch square. Okay. We're still not done. We still have to calculate our load carrying capacity. Correct? So the load carrying capacity based on yielding. Let's start with so what you do for yielding, you take 0.9, that's your factor. You take Fy times of A gross. So that is nothing but 0.9. Fy is your 36, and A gross for one angle was 6.8. If you do that, you see 244 point, sorry, 220. This would be 220 kips. Okay. Now let's talk about rupture. Rupture for that particular path with the least area. So rupture is 0.75 P with your FU value and your least A, A effective value. So A net was this much, and since all the legs, since both the legs are connected to the fasteners here and the fasteners there, then your U value, as we talked about in our previous session, we talked about different U values for different connection types. U will be 1.0 when both the legs of a tension member are connected. Okay, so that means your A effective is nothing but A net times of U. Since U is 1, that is A net. So A effective is nothing but A net. So you take 0.75 times of your 58 times of your net area minimum is that much. So 5.065. So when you multiply all these things, you find out this also to be, unfortunately or unfortunately, so many kips. So the strength of the connection is the least of these two values. In this case, they are both the same. So phi times of Pn is the strength of the connection is 220 kips in this case. Okay. So hopefully that makes things clear, right? One more time, if you have a plate like that and you have zigzag boards like this, right? To find the net area, you will have to figure out how many different failure paths are there. This might be one failure path. Um, this might be another failure path, right? And then you calculate the fail. I mean, for the black failure path here, you take a gross area minus 2 times the diameter of the hole times of the thickness of the plate, right? And that is your A net. Whereas for the red path here, because there are two oblique planes, what you do is you take your gross area, you times 2 times of one, two, three holes. So 3 times of the diameter of the hole times the thickness of the web, right? But you come back and add 1 s squared by 2g for that, s squared by 2g1 maybe, or s1 squared by 2g1, and then another s squared by 2g for this, s2 squared by 2g 4g, okay, times of thickness. That's how you compute net area for oblique paths, and then pick up the minimum between this and that, and then start doing your regular computations that we talked about extensively in our previous session. Okay, so that completes the example that I wanted to cover on tension members. Hopefully, pretty straightforward. If you have not watched the previous session, go ahead and watch it, because there we talk about how you can calculate a net, a gross, shear lag factors for different cross sections, rupture strength, and yield.